Right, in the next slide, I'm going to try to get a sense for the size of the Earth. I'm going to make a scale model of our Earth, Moon, and Sun system. So what I've got is I'm going to represent the whole Earth by this little squeeze toy that you see, and I'm going to try to attempt to make a scale model of the whole solar system. Okay, now here's my scale model. In order to get my numbers correct, I've got to sit down and work out what the scale size is in relationship to the real Earth. Okay, let me just change the color here. So my real Earth the full radius of the Earth is 6,371 kilometers. So that means that the diameter of the Earth is equal to 12,742 kilometers. My squeeze toy, the ball of the Earth that I have here, is only 6 centimeters across. So I'm going to attempt to calculate a scale model. So therefore, the scale factoring size would be the model size ball, which is 6 centimeters, divided by the 12,742 kilometers. Now these two numbers have to be in the same units in order to get a true scale. So I will then take the 6 in order to turn the 12,742 kilometers into centimeters. My number is going to be 12,742 times 10 to the power of 5. Okay, because there's 10 to the power of 5 centimeters in a kilometer. So my scale size then comes out to be 4.71 times 10 to the minus 9. That's my scaling factor. So that means that I'm going to take every other object in the solar system and I'm going to multiply it by the same scaling factor, and that will allow me to make a model of the solar system itself. Okay, well, let's consider then the other objects. So first of all, let's look at the moon. How big would the moon be in comparison to the Earth? If the Earth is the size of a squeeze toy here, roughly how big would the moon be? What do you think? Would the moon be bigger than the Earth? Well, how big would it be in comparison to the Earth? Okay, so I'm going to try to represent the Earth by this squeeze toy here. It's about 6 centimeters across. So if the Earth were, shrink it down to this size, if the Earth were this size, how big would the moon be by comparison? It turns out that the moon would be about this big by comparison. I've got a little bit of Play-Doh here. Okay, well, let's have a look and see how big the moon actually is in comparison to the Earth. So the actual moon's real radius is 1,737 kilometers. That means that the diameter of the moon is equal to 3,474 kilometers. Okay, so my scale size for the moon is that actual value, 3,474 kilometers, and then I multiply that by my scaling factor, 4.71 times 10 to the minus 9, and that will give me a real size of 0.0000164 kilometers, which works out to be 1.64 centimeters. What about the distance to the moon? Now, in terms of where the moon is in relationship to the Earth, well, where would it be? Would this be how far away the moon would be? Or do you think this would be how far away the moon would be in comparison? Well, it turns out that the moon would actually be quite a distance away to scale. I've got a bar here to represent the moon's distance to scale in respect of the Earth. So here is the representation. So if the Earth were 6 centimeters across and the moon were, I have to go back quite far here to get the whole thing in at the same time. So here is here's the Earth to scale. That would be how far away the moon would be, and that distance. It took the Apollo astronauts 4 days to travel that distance in space. If you plug that into your scale model, you'll find out that that comes out to be 1.81 meters away. That's how far away the moon would be. Then, in comparison to the sun, let's have a look at it. The size of the sun, the actual diameter of the sun, how big would it be in comparison to the moon and the Earth? Well, its real diameter is 1,391,980 kilometers. If you multiply that by the scaling factor, you'll find out that the diameter of the sun to scale would be 6.55 meters across. That's pretty crazy. So if the Earth is a squeeze toy and the moon is this tiny little piece of Play-Doh, then you'll find out that the sun's diameter is approximately 3.6 times the distance between the Earth and the moon. Now, it took the Apollo astronauts 4 days to go to the moon in a spaceship traveling faster than anybody else had traveled at. The diameter of the sun is nearly 4 times larger than that, which is pretty crazy. If we then consider the distance to the sun, the sun is 149.6 million kilometers away. That's called 1 astronomical unit. In old money, in old units, that's roughly 93 million miles. Now, if we multiply that by the scaling factor, that comes out to be 704 meters away. So if the Earth were the size of the squeeze toy, the moon would be 1.8 meters away, and it would be the size of this little piece of Play-Doh. The sun would be 6.5 meters across, and it would be roughly 700 miles away, or 700 meters away, sorry. Now, the farthest reaches of our solar system, if we take into account the distance of Pluto, Pluto would be roughly the size of this little model that I've got. There's roughly where it is. Now, where would Pluto be to scale? Pluto would be about 17.5 miles away from the Earth. So how difficult would it be to try to find this when it's 17.5 miles away? Pretty difficult to do. All right. Now, what we then try to do is we try to represent. Well, we don't really deal with miles and meters anymore, because that becomes ridiculously big numbers when you deal with the whole solar system. So what I have here is I've got a scale model of the whole solar system on this slide. The distance to the sun, so the distance to the sun is called 1 astronomical unit, 1 AU. That's 93 million miles, or 150 million kilometers. So there's the representation of the distance to the sun. Venus is about 0.7 astronomical units from the sun, and Mercury, the closest planet, is around about 0.4 astronomical units from the sun. If we then zoom out, this large square here zooms into this tiny little square in the center of the bigger diagram. The full range of our solar system, if we take the orbit of Pluto, from one side of it to the other, is roughly about 80 astronomical units. So that gives you a size of the whole solar system. Now, whenever you're dealing with really, really large distances, even astronomical units are not very, very useful. For instance, if you take the next star out from the sun, it's a star called Proxima Centauri. It's the next nearest star. It is a whopping distance away. The sun is 1 astronomical unit away from us, and Proxima Centauri is roughly 271,936 astronomical units away. That's crazy in terms of the distance to the sun. So the next nearest star is more than 250,000 times further away than the sun is. Right, so what does that sort of represent in terms of our scale model? If we were to put that to scale, that would be the equivalent of 118,983 miles away. So on our scale model of the solar system, the Earth is the size of the squeeze toy. Pluto is about 17.5 miles away. The next nearest star is 118, almost 119,000 miles away. So what astronomers do is they try to talk about the distances, not in terms of miles, not in terms of meters or kilometers, or even astronomical units. When you start dealing with really, really large distances in space, astronomers start dealing with distances in terms of the speed of light. Light is the fastest thing that there is in the universe. If you're traveling at the speed of light, you could cover 186,000 miles in a single second. And that means if you could travel at the speed of light, you'd be able to fly around the world 7 times in 1 second, which is one of the reasons why you're able to watch things live on TV from one side of the planet to the next, because you can transmit the signals around the planet very, very easily. It's pretty much instantaneous. Now, when you're dealing with distances off the planet, though, the speed of light takes a long time to travel the distances involved. For instance, how far does light travel in 1 year? Well, 1 light year, that's the distance light travels in a year, is very, very, very large. It's approximately 63,240 astronomical units. So if you were traveling at the speed of light, you could fly around the world about 7 times in 1 second. You could fly to the moon in about 1 1/4 seconds. You could travel to the sun in about 8 minutes. You could catch up with the Voyager 1 space probe in about 17 hours. And it's been traveling since 1977. If you continue to travel at that distance, you'll find out that the nearest star, Proxima Centauri, is around 4.3 light years away. So to travel to that star at the speed of light, it would take you 4.3 years. Which means when you look at that star in the nighttime sky, you're actually seeing it as it was 4.3 years ago, because it takes light from that star that amount of time to make it to the Earth. Imagine what it would be like if you were trying to communicate with an alien orbiting around the star Proxima Centauri. If you sent a message to them, say for instance you said hello, it would take 4.3 years for the message to get to the star. If they immediately responded to the message, it would take another 4 years for the message to get back again. So an immediate conversation with an alien around Proxima Centauri would take over 8.5 years just to say hello to each other. Pretty crazy stuff. So what astronomers do is they represent distances, vast distances in space, in terms of how long it would take you at the speed of light to get there.